name is Loay Ben Zakta. Today, me and my partner Tan Ajar will present a optical communication system. I will start with the transmission part of this system, and my partner will continue afterwards with the receiver part. In the transmission unit, we have three main circuits. Firstly, we have the microphone driver circuit, which can be seen from this schematic, where this will be the microphone biased with a resistor and a capacitor. After that, this capacitor will convert our voiced electrical signal to a voltage analog signal, and this signal will be amplified by this op-amp as shown here. After that, we need to control the audio which we are inputting to the system. So we have an automatic gain control here in the second circuit in this unit, which works as follows. It takes the input from the microphone driver, and it detects the peak using this circuit here, using these two diodes and the BGT. After that, this peak is forward to this the second BGT, and according to the peak, it will determine the current flowing across this BGT. This current will flow across these two germanium diodes, which will introduce an impedance seen from this side, and this impedance will determine the voltage drop at this node. And so this part of the circuit acts like a feedback network, and accordingly it will control the gain. This gain then, the controlled gain, will be summed with our reference voltage, which will be a 30 kilohertz signal with around a 3 volts peak to peak, and they will be summed up using this summation amplifier as seen in this schematic. After that, this summation signal will be sent to the third circuit of this unit, and the aim of the circuit is to convert our voltage information to current by using a transconductance amplifier. In this circuit, we use the linearity of the op-amp, and the signal will be fed to the non-inverting node of the op-amp, and due to the linearity, the plus side will be the same as the negative side, so this voltage will appear here. This resistor is just for protection purposes. No current will be passing through this R18, and the entire voltage of our sign out, which is the summation of our audio and the reference signal, will appear at this node. And this will introduce a current across this resistor, which will be the current in the source side of this MOSFET. And due to the characteristics of the MOSFET, the source current will equal to the drain current, so which we will have our LED here, so the current of the LED will be the current across this R50. So by this way, we have like a transconductance relationship. So we converted our voltage to current, and it will be, after that, it will be modulated into light and sent to the medium, which is air, to the receiver part. The receiver part now, my partner Tan will discuss it in detail.
Hello everybody, my name is Tan Çatayacar. I'm a third year EE student, and today I will be presenting my receiver circuit with Loay. First, we get the light signals by a phototransistor, which is biased by a 10K resistor, and we extract the AC signal by a high pass filter, and we selected the high pass filter with a 150 Hertz kernel frequency, so that we could eliminate 50 and 100 Hertz means voltage noise. And then we have another second order high pass filter design to active filter design to eliminate our audio signal. This has a kernel frequency of 20 kilohertz, and our reference voltage is at signal is at 30 kilohertz, so that it's we assure that they are filtered nicely. And then there's a half bridge rectifier to detect the peak amplitude of our reference signal. Then this reference signal is passed through this comparator network. There are 4 different levels of signal intensity. Depending on the signal levels, the RGB here has different states, and we create states such that it would generate green for the most powerful signals, and red for the least powerful signals, and intermediate color values for but with distinct transitions for the middle states. We control the blue channel with two op-amps, and we control the other two channels with just one op-amp. They are simple. With two op-amps, we do a voltage division, and that's how we open the blue channel right in the between the middle region, and then close it back when we are at the most powerful state. And then we also, from our original signal, we also extract our audio signal with a low pass filter design. We already have filtered the lower part of 150 kilohertz. Now we filter the high frequency reference signal, which has a corner. This filter has a corner frequency of 3 kilohertz, so we only get our audio signal. And then the audio signal is compared with a comparator with a DC value of close to 14-ish volts. This is to ensure that to measure that our signal is not clipping. If it's clipping, it should be, let's say, our audio signal should go in positive cycles above 14 volts. If this occurs, that starts to light up, but since it's in like higher than 10 hertz, our eyes see it as a bright LED. So that's how we detect clipping. And then we have our driver circuit. Finally, the driver circuit has an on-off switch, MOSFET, which is controlled by the reference RMS logic, level logic. And if the reference signal is below a threshold, then this circuit is cut off. It's not on. If there is an audio signal, it would not generate any current from the speaker. But if we are above a certain threshold, then this circuit operates. We use the B class amplifier design with a calibrated middle resistor for the bias. We have two small signal input, and then we generate currents, which are we have two complementary BJTs in push-pull configuration, so that we generate a symmetric sine wave AC current passing from the speaker. That's how we achieve more efficient operation compared to class A amplification. But in this result, we also introduce some harmonics which could be ignored. Thanks for listening to me.